And now it's recording. Okay, so oh no, if these rooms have something like a designated place for pens.
No idea. I have one if you want to borrow.
Yeah, that would be great. Otherwise, I have to go back to my office. Thanks. Cool. Yeah, I just basically picked exam exercises by random and looked a bit through it, and I think it might make more sense to do the first half of the lecture now, more or less, and do the more advanced stuff next week, so everyone has more of a chance to learn about Laplace transformation and things like this. So I actually picked some exercises just from the last exam in August 21. And they were about differentiability questions. If you have something in particular, like some exercise you were looking at and you want to see solved here with comments, we can also try to do that. So, I mean, this is just me picking something and guessing that it might help, but yeah, feel free to change the course of our meeting here. Okay, so I'll start with the first exercise. The last exam actually has at least 2 on differentiability. And the first one is also about sequences and continuity in a way. So, I mean, that's, I guess, a good way to get started. So this is from the exam 21.8, exercise 1. And I mean, you can open it in your computers if you have one. Otherwise, I just read it to you.
Which exam was it, say?
This one, 21.8. So the folders should be named after the months the exam happened in, I guess. Can anybody confirm? I can just look at the link. Yeah, it's the folders are named like this. Okay, so let's have a look at it. I have to manage a bit my screen size here. And the very weird way of rendering PDFs on GitHub. Okay, so we say a function is continuous at an interior point C of its domain if blah, 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 some limit exists, and otherwise we say it's discontinuous, and then it goes on. Differentiability can now be defined using our notion of continuity. And the first exercise is to basically explain the notation. So it says, explain the typing and scoping rules for the lim construction, and specifies a bit what can be written before and after the arrow, etc. Okay, so what is meant by that is we have a limit like this. Maybe I should pay attention. I write the exact same notation, which I didn't. Sorry, I dropped a bit to differentiability. So it says x goes to c, and here we have x, and let me just remind the context of it. Okay, it just asks for limit. Yeah, so yeah, I mean, I should replace this one. Let's say just with E to say we have one abstract expression, right? And the things we need to explain now are this, this, and this. So we should say what are its types and what might be other constraints. Can't express with types, so let's get started. So maybe I just circle some parts and say this is 1, this is 2, and this is 3. So 1. Any idea what that might be in general? Yeah, please just say something aloud.
I guess it's a value of a subset of reads.
I mean, that's what we should think about it, that this X is a real number, so it might be constrained in some subset, yes, but from the syntactic viewpoint, that's not what the exercise wants from us. So it says explain the typing. Okay, that's something you did, very good, because I mean, this X is something of type real. So I mean, that's something we can certainly say. And let's make just this identification. So we're absolutely sure about what we are talking about. So it's certainly this, and X might be constrained to a subset, but let's think about this one later. Okay. Hey. Okay. So if it would just be something I can write here that has to be a real number, could I write something like this? Does it make sense? So this is supposed to be a 5. Would this check as valid syntax for you? No, right? So no, this is not okay. So no. Okay, so I mean, we figured out this should be somehow of type real or from some subset, but we have to say something else. And what is it, what we have to say? It has to be a variable. So I mean, that's a bit tricky. I mean, in type theory, so in Haskell, when you write down a program, you learn very early there are terms and types. So when you write down a function definition, you give a term that has the type that you maybe earlier said it should have. But there are distinctions. So if Haskell would be a less expressive language, it might be that you could only write definitions that correspond directly to a lambda expression. So something like this. And then this X can only be like a name. So it can't be like something like 5. So it's not a general term. It is something that can be used like a term, but yeah, you're not allowed to use other terms in this place in general. And I mean, that's the same restriction that we have here. So we have to say X is a variable. So it's a special term is a variable of type. Yeah, and now that's something more specific. Yeah, it has to be in the domain of F. Also, someone online noticed, right? So it can be constricted to be within a subset, and we can also exclude C. For U, some subset of the type of freeze. So that's what I would say here. I mean, in general, the question is a bit vague. It is not like compute this equation, solve for X. So you have a bit of room here of what your answer can be like. But I mean, you can't just say it's a term of type real. That would be false. That cannot be a general term here. It's a variable. Okay. And in Haskell, for example, we have a bit more freedom with syntax. We can also pattern match. For example, if we have a type of pairs, so let's just say we have a function like this, from R times R to R, then depends a bit how we define this, but it would be okay to use something like this on the left side. And I mean, that's also something where what we could use here. So that's okay. So that's something we could add here, but I think that's not the most relevant point. And simple pattern matchings are allowed. And I mean, that fits with the mass notion. There it would be okay, like to say, let a pair of variables go to some C, which is a pair. So could also, if we do something like this, I mean, we could say n-dimensional here. Okay, so that's what I think should be said about what in the text told us that C is not in the domain of F. Aha, good question. So why did I do this? I mean, that makes the limit actually stronger. So if we yeah, okay, it's a bit questionable if X is really supposed to be unequal to C, or if we are just allowed to assume it's unequal to C. If you look at the definition of the derivative, maybe for comparison, let's have it over here. There I have this h which goes to 0, and I divide by h. And that's of course only something I can do if h is non-zero. So I'm at least allowed to assume that my h doesn't assume this value here. It just converges to it. So I think for completeness, that should be mentioned. I mean, I could just also say my term here is only defined. Yeah.
I was thinking, sometimes when you compute the derivative, you can simplify the expression to remove h, and then you can plug in x, h equal to like c, for example.
Yes.
So.
Okay, good point. Maybe it's better to say it without it, and the user has the freedom to choose U. And then I can say my U doesn't include C. So, I mean, then I'm allowed to do your trick of dividing by age and then saying, okay, now I can just plug in 0. But I mean, you have two ways of finishing off something where you divide it by age. I mean, if you just have like this, you could also say, I prove this one time as a theorem that this will be 0, and then kind of use this theorem and say your limit doesn't include C. Yeah. There's a bit of choice.
You're not really supposed to plug in 0 because H should only approach 0, so it should never be 0.
Yeah.
But you just use it to like see what value you get.
Yeah, I mean at this point you kind of see it, but yeah, you actually have to prove it. Yeah. At some point that this will actually give you 0, which is just instantiating the definition and of convergence, noticing that everything is okay. A trivial proof if you're used to proving, but yeah, something that should be settled. Yeah, and I mean, if we say this is a theorem, then we should again say without C. Okay. Any more questions? Ah, no, it's not. It's still the same question. Okay, good. One part solved. C. So what is C?
Constant.
C is a constant. Next question, constant on what? With respect to what? So constant is good, but
the same type as X. But constant. So a constant real.
It's a constant real. I mean, it might vary in some other stuff we have somewhere else, but with respect to this, it's a constant. And we could say C is not allowed to depend on X. I guess that's what you mean. So if it's constant with respect to X. So you have to pick one fixed number, that's the intuition. And then we approach this fixed number with our variable X here. Okay, so C does not depend on X. So in this sense, it's constant. And or alternative formulation does not contain X, so we're not allowed to use X when we construct C. I don't know, whatever works for you. And now to the type. You said same type as X. I almost agree. That works for a lot of things. But for example, if we have a function which is defined on this interval, are we allowed to use, for example, 1, which is not included here, as something we put in a limit? Yeah. So the answer is all the points we can kind of reach by series inside our domain of definition. Yeah.
How would you state that more specifically?
Yes, so there are two ways to say this, I guess, which are the most basic ones. So one is C is of type closure of U, but I don't know if you know this notation or what it means. And so forget about it. And
is it like the penalty type?
No, that's that's just from math analysis. So, but yeah, I guess we didn't talk about that in the lecture. So we can say C is Yeah, right, a limit point. I guess that's something Patrick mentioned as a limit point of U. So what does it mean, limit point? Let's call it D in our surrounding space. I guess you're allowed to forget about the N if it distracts you. D is a limit point of U if there is a sequence in U that converges to D. So that's a definition, and maybe here's a picture. It's better to have those things like two-dimensional. So let's just say we have a point here. So this is D, and this is an open subset. So it's like this one where you don't include the boundary. And this point just sits outside of our U, touches it, but is not inside, like the one here. But we can have a sequence which converges to that one. So for example, in this case, I can write down such a sequence. So 1 minus 1 over n converges to 1. But all these members of the sequence are contained inside this. So let's just say that's our U here for our example over here. And this is a sequence. Around. And then we have AN is in U. So you can check because, yeah, maybe let's say n plus 1 to be safe. And say our sequence starts at 1. Or let's just say you start at 0, because I guess that was the convention, and add 2 here. Then we have a sequence which starts with 1/2. So this is what AN looks like. Then it's 1 minus 1/3, and you can check it's getting closer to 1, but it doesn't leave U. So it's exactly what we asked for. Sequence in U that converges to 1. And I don't know if you are now confused by this, we could also talk some more about this and maybe reason together why this is a sequence that converges to 1. Yeah. I don't know what you need. But maybe we just say, okay, limiting point, and just finish off our task here. So last one. So this was part 2 of our expression, and now part 3 is E. What is it allowed to be?
That's an expression.
It's some expression, yeah. As a function, what is it? Function from R to R is good. You can also be a bit more fine-grained. So here we had a domain of definition. I even said R to the n, but don't have to be that general. Okay, so I would say a function from U to R. So starting domain of definition. And otherwise, can we say?
Be a function to R.
No, not really. We could also say it's a function to some subset of R, or a function to some subset of R to the M, or whatnot. But yeah, I guess with subset of R, we are general enough for our context here. So we could start with this and say E is of type U2 V, where V is some subset of R. Let's just keep it that general. And now we should also talk a bit about X. So, I mean, we have this variable X here, and I guess you all know you can use it inside here. And that's something we should mention. So it's a thing that depends on X. So E is allowed to depend on X or contain X or be a function in X, whatever works best for you. Okay, so I would say that solves the first part of this exercise. And let me look into the internet, what people say. I guess it's more or less what we, yeah, how come we dropped the power? Yeah, we dropped it here. I mean, here we could also say we take some power. Yeah. Yeah, I guess that's questions from the internet. Okay, so we could continue doing more stuff in this direction, or we make a digression and repeat limit of a sequence. I don't know, any special interests? I guess not. Oh, okay. Yeah, I'll just continue with the exercise. So now it says in this expression using a limit where you define the derivative of a function, give the types of all things involved, basically. So yeah, let's do that. Okay, so part 2 is we look at the expression that defines the derivative of a function at some point. So we have x plus h here minus f of x divided by h. Okay, yeah. And we are asked to explain the type of these symbols. I guess we don't have to talk about the 0. Yes. And we are also asked to explain our reasoning. So h is from the domain of f. I think the f is a bit restricted here. Blah, blah, blah. Ah, no, it doesn't say so. So, okay. Good. So let's, yeah, what's the best point to start with? Maybe f. Okay, so we plug in values to f and we divide by something. So any ideas how that turns into a constraint of f? So, I mean, we have this h. We don't know yet what it is, but here we divide by it. And
0. So it can't be 0.
It can't be 0. Yeah, that's something we enforced earlier in our constraints on how the limit construct can be used. Yeah, it's something we're already done with, but dividing by it means we don't have like some multi-dimensional thing or something going on, because then we wouldn't know what division means. So f has to be a function to the reals. And then we also see h gets more or less plugged into f, so it's a function from the reals. So f has to be of type this, or let's say something like this for subsets of the reals. Right? Because we are asked to explain. Okay, someone is. No to the internet, C cannot be in the domain. We excluded it. C cannot be X, but why not? E can have C in its domain. Yeah. I hope so. Okay. Yeah, because we divide a value. I mean, we divide values of f. Let's say that more or less. I mean, we first subtract and then divide. Maybe let's just say we divide by h. Divide by h. So the involved numbers must be reals, and this expression x plus h must be of type R. So that's maybe a bit much text. I don't think you have to be that verbose, but you have to write something that is an argument if you're asked to explain something in an exercise. And x plus h must be of type R, since h is. So domain of f must be a subset of the reals. Okay. Good. So we cleared f, and now I guess the other stuff is kind of clear. So x has to be something from the domain of f, at least. So x is in U, and h, are we asked to explain that, by the way? H, yes, we should also explain h. Okay, something we kind of already did over here, but why not? H is in U, but h is also not 0. So we said over here, by excluding C. Okay, and now only f prime is left. So that's again a bit more tricky. So what's the type of f prime?
Shouldn't it be the same as that?
Good idea. Why not?
For where it's not differentiable.
good point. Yes. So we have to exclude that. So
some instead of arms.
So I mean, set x and y here for the full generality. So we have some x prime, and let's say for now 2 question mark, and x prime is I can just use subset notation, is all the x where f is differentiable. Yeah, but what about the codomain? Maybe the same as f or something else. Just reals for some reason. Who is for y? Who is against y? Nobody wants to say anything. Yeah, I mean, it's a bit tricky.
It doesn't have to be all of y, does it?
It doesn't have to be all of y, but on the other hand, we are just asked to give a typing that works. So we don't need to aim for a really optimal one. Yeah, so the internet suggested y. To be more precise, Anaya suggested y. So that's a good idea. That's, by the way, also what's in the solution to the exercise, but it's wrong. Because, example, we can have a function, let's say, from 1, 0 to 1, 0. Everything nice and real. Let's say it's everywhere differentiable. And it looks, that's a bit small. And looks like following. So like this. So it's very small. Oh, and then it has a bump like this. Yeah. Okay. So what will the derivative look like?
It can be negative even though the original function wasn't.
Yeah, I mean here it is negative and it's quite big. So I mean, if this is 1, then this is about 1/4 maybe, and our function managed to go from here to here just in a quarter. That means its derivative, its slope, must be around 4 here when it goes up. So the derivative will look something like, something not fitting into this graph. So it will look like this. So it starts out very low, then it goes up to 4, down to 0 again, and then down to -4, and then up again. And then we are only at 1. Yeah, so no, y doesn't work. And I mean, the only thing we can say here in general, without using dependent types or whatnot, is it has to go to the reals.
That's That's not a very satisfying answer to give. I think.
Yeah, I mean, if you want to be in an exam, don't spend your time on finding the best answer here, of course. But I mean, if you want to find the best answer, we can just look at this and say, aha, what are the boundaries here? So it's just the max and the min of the derivative. Right, so we could say something like it goes to y prime. So maybe I even put it on a different board because it's something I guess you are not expected to come up with when you solve an exercise just about typing like this. And here you could say it's the interval closed from max f prime of x for x in u, and I'm always mixing it up, for little x in big X, and it oh no, that's doing, so it's min, and here's max, of course. So I mean, that's kind of the optimal thing you can say about it. But it's a bit weird as a type restriction if you have to compute so much. But yeah, in a dependently typed language, if you implement something like this, you could do this if you want to use your derivative later and have some bounds about it. But nobody, I guess, would do it like this, because also in a dependently typed language, where you could do types like this, you still would do types like this and then prove a theory which tells you this. And so, yeah. So that's a bit unrealistic as typing, but realistic as stating something in math. Okay. Good questions from the internet. So someone asked, Campus asked, would it be wrong to just say from R to R here? No, you can say this. It's a correct typing. I mean, it's not. No, you cannot. Sorry. Yeah, good point. I mean, you can't say this here for the derivative, because you don't know if you can plug in values where f is not differentiable. So here it's actually a problem.
Is it correct for f though?
I mean, for f, we are kind of imagining a bit what is intended by the exercise.
Yeah.
So I don't really know how you could say it's wrong to just say R here.
Yeah. But if we see this kind of question on the exam, for example, is it safe to assume that if continuity and derivatives are involved, that we're only in the real case and not in complex or some higher dimensions? Yeah,
I would say it's safe to assume you're in the one-dimensional real case, but you should treat the case where you have subsets, because that's something that happened all the time, and that's something you need to make sensible definitions. So I mean, this is the generic case for functions. Yeah, some, I guess, not so serious suggestion. Type f from R to maybe R. Yeah, yeah. I don't know. I mean, if you use maybe, it's a subtle distinction. If your function throws an error on something, or if you use maybe. If you use maybe, you have to actually decide if something is in your domain. So you need to compute, should I say none, or should I say something and compute it? And that's actually something extra. So that's asking more of your type than just saying I have from R to R, but sometimes there will be an exception. Yeah. Okay, yeah, so this, and I should fix the old solution where it says y here, which says that here is not, doesn't work in general. Yeah, prove that s is, okay, now we get a particular function and do some differential stuff with it. Unless you still have questions about that or something else, we'll just continue. Or should we make a break? I learned there's a custom to have a break. Yeah, I guess it's a good point for a break. So let's have 10 minutes break. I will inform everyone. So until 14.
Do you still have time for a question?
Yeah, sure.
You maybe talked about regarding the first exercise. Yeah. You said that C excludes C from the domain of X, but you don't necessarily need to do that, right? Because I guess it doesn't make much sense to do this when the function is defined in C, but you still could make such an expression, right?
Yes.
So that's like an extra assumption about when you want to use a limit, isn't it? Because I guess you could do, it's still okay to write X to say 5 for the function X. That's still a valid expression. It's still as 5, but it's still okay to do that. Because or say 0. But if I did that, it's not okay. But I guess it could still be in the domain.
Yeah, I mean, the possible values that X can have.
Yeah.
So, I mean, the type of X tells us how we can use X here.
Yeah.
So, I mean, this is only to allow us to do something like this.
Yeah.
But it doesn't forbid us from to do other stuff.
Yeah.
So it's something we have, not something we lose.
Yeah, fair enough.
Yeah, and I mean for the definition of limit, you need sequences that come from outside towards 0 anyway. So you're safe to exclude all the sequences where you don't have this value, and you lose nothing doing it.
Yeah, fair enough.
Yeah.
Nej, det spelar ingen roll vad X är för någonting egentligen.
Men du är fri att använda en typ som inte innehåller någon.
Ja, det är det sant. Ja.
Det är ingenting man kan vara.
Nej, jag tycker de här uppgifterna är så svåra och liksom entydiga vad vi vill ha.
Did you say that you're studying native languages?
Yes, I use Acta a lot, which is developed here. And I guess it's one of the reasons why I am here, why I came to Gothenburg. And I mean, the main reason is Thierry Coquard, if you heard of him. It's a professor here. Yeah, and he's important in the field that I work in. He invented some stuff, that I like.
Like dependent languages are super interesting, and I'm thinking just like there's a tiny peek at it. Are there like, I guess like that's better for proofing stuff, so more rather than like general programming, right? Would you recommend like English or something if you want to try out using it in practice, or are there any other languages that are more well suited?
I mean, you can use Actor definitely for like real programming.
Yeah.
I didn't do that much, but I did it. I think it's actually a good way of programming. What's a bit annoying is that you really have to define functions in a mathematical sense. That means you have to write it down in a way that the termination checker accepts it. So you can only write down functions where it's obvious that they terminate. And that's a pretty strong restriction. But I mean, unless you work in logic or writing tile checkers yourself or something like this, most of the time you only write functions that obviously terminate. So you don't do everything else. But if you write a type checker, this is really difficult, because if you write down a definition of a type checker function where it is obvious in this way that it terminates, you kind of have proved advanced properties about checkers. So that there's some stuff it makes very difficult, but like for everyday life stuff where you just want to calculate something, or you usually want stuff to terminate. So in practice, some people get around these issues. So for example, there's F star, which has an extra type for function which are total, like that are the ones where you have to make sure they terminate, and other functions which might not be total. That's like a common pattern. I think also OCaml has it. That's not dependently typed. It's very valid working language. I can say it's working better than Haskell.
Yeah, would be nice to try out. I can say this in German,
but I'm saying it kind of on the internet because but yeah.
But OCaml isn't as pure as Haskell. You can do side effects easier, if I'm not mistaken.
Yeah, I'm not sure about the theory of it, but I mean, in practice, it kind of feels like the same what you would do in Haskell. You can write sequences of instructions that works like an imperative language, but you have to be aware of the fixes like monads and stuff like this. Make it possible. Only up to some degree. Still learn it by looking at it. Yeah, Idris, I think is nice.
Very similar to Haskell. It's very similar to Haskell syntax-wise, but I guess most ML languages are.
Yeah, I see one problem with dependently typed languages, at least with the current implementation, and that is you don't know if the type checking will be fast enough for the project. So that would be my main worry if I decide I use a dependently typed language to code up some big software or this for myself. I mean, I wouldn't ever do it in a commercial application where other people might be forced to learn this language if they want to. That's a different problem. But the type checking speed is actually something I'm worried about, but it's not theoretical. I think it's only practical because it's very hard to write a language like this
works that, and humankind kind of has just invented this, and figuring out lots of stuff, how to make it better, and sort it out in nicer ways. Yeah, I guess this will be solved, and then you can really master computer languages. So I use it a lot for formalization, and it actually happens from time to time that it gets very slow in type checking. I don't understand why. I mean, I'm also not deep. I don't have deep knowledge of the technology. I don't write type checkers myself. At least not real ones like this or types on this. But it's definitely worth checking out.
Yeah, it would be fun to try. So I guess it's a bit scary when you're not that familiar with Haskell either, whenever you like monad transformations and stuff like that. And I think it gets a bit scary to start with dependent types as well. I don't know, to get into writing more functional code. I think Haskell is such a nice language to work with, but it's not that nice to when implementing actual programs. I think it feels more well suited for things like this course when you're modeling maths or stuff like that.
Yeah, I mean, it's very useful if you have something where you have these syntax trees. You can use this.
Yeah, if you want to
special data types, then it's just very good. And I actually, in the real world, I used Scala, not Haskell, for something I knew I had a lot of syntax like this.
I've been writing a lot of Rust, and it's really strange to work in a language that doesn't have array data types.
Yes. Yeah, if you once learned about them, you will miss them in all the other languages. Okay, I would say we continue just with the next part of this exercise. Which is about some specific function S. So I will give you the definition from the text. Yeah, so this is what we have given. We have a function S from R to R, no subsets here. And it is defined like this. So S of X is minus x squared for x smaller equal 0, and S x is x squared for x bigger than 0. Okay. Negative x and yeah, okay, it's not exactly the text from the exercise. It would be like this, which doesn't matter. Okay, and we are asked now to do what? We are asked in part C to prove that S is differentiable at all x with the standard definition. And we should define a closed form for x, for S prime. So C. Okay, so what do we need to do? Well, we can start by plugging in. We are supposed to use this definition and show it's differentiable. And the definition says, it's given here in the text, a function is differentiable if at x, if this limit exists, of course, and we are supposed to show it for any x. So it's a bit more verbose here, and we would have to write it. So we have to show limit h to 0 s x plus h minus sx over h exists for all x in R. So that means it's everywhere in R differentiable. Okay, so first obvious step, we just try to plug in stuff, which is not really easy here because we have this case distinction and it's not so clear how we can manage it. What would you do?
Deal with them separately, right?
We can try to deal with the cases separately, yes.
Since here, like h approaches 0, you have like a left side of the function and the right side, which could be like the two functions, and you can see where they meet.
Yeah. So you say the case where
when like you approach 0 from the negative side, and you approach 0 from the positive side, you have two functions.
yeah. Maybe we should look at it a bit more in detail. I mean, I see where what you say is right, but we have to be a bit careful here. We still have this x from R, and that's what we plug in into S. So one's x plus h and one's x. So our x might be far away from 0, and then this all doesn't play a role. So we're just in one case, basically. Yeah. And this basically is a bit tricky. Are you with me? Do you know what I mean? So, I mean, maybe I should draw a picture. So, kind of have 0. Our function, maybe I should draw it, looks like this. And here is the evil case distinction, which messes up just plugging stuff in. But if we are outside, this is just x squared. And if we have some series which approaches this point, and this is what this definition is about, then this case distinction is far away, it doesn't matter. So, I mean, the question is now, how can we say this? So I would suggest the following case distinctions, but it could be done in different ways, I guess. So if we do it with case distinctions, I would do these 3. And in these cases, you can say something like, this case distinction doesn't really matter. I mean, one way, how I would say it is x plus h, if you have x is smaller than 0, then x plus h is also smaller than 0 for almost, oh, that's not how you write almost, sorry, for almost all h, if you know this terminology. If you don't,
Never heard almost before in a math concept.
Ah, really? Okay, yeah. What it means is only finitely many, if I have a series, only finitely many, at most finitely many will not satisfy this condition. So if you, I mean, this is a series really, which goes infinitely on, and this says if you walk a bit at some point, this condition will hold, and then it will never stop holding. This is because h converges to 0. So that's one way to say it, but I guess it's not your way because you didn't learn it, but so let's maybe put it like this. Yeah, I mean, one way to say it would be we can restrict S then to some smaller domain of definition. So we could look at, maybe let's call it T from this domain. With Tx, it's x, Sx, all of here. So we just look at one branch. And then we can plug in values. So that would be one way to do it. And that way would work. There is a different one. I want to show you both. So there are at least two good ways to solve it. And maybe you're more comfortable with one of them. So what you also can do, and I think this is actually what I would do, is to write this case distinction as a function and kind of use this to forget about it. So you could say this function S is really sine function. So sine, not like cosine sine, but sine like this, if you heard of this. So that would be a way to rewrite it and kind of encapsulate the case distinction, unless you need it. Then you can at least plug in values here and kind of calculate it. But I think the suggested way is actually to do something like this. I mean, even if you don't come up with this thing and say, okay, I could as well take another function which is only defined in this third, you could say something, if x is smaller than 0, I certainly can just plug in this set. I guess you could get away with this. Okay, so what can we do? We can plug in this definition. So here we have x plus h squared minus x squared over h. And should we do it with limit or without? I don't know. Let's just write it in front everywhere so it's clear what we are doing. Yeah, and now I just have to calculate what it does, what does it do. Yeah, I guess I put a minus in front, something like this, and get x squared plus 2hx plus h squared. And, yeah, minus x squared over h. And yeah, continue calculating because this, I guess this is something you're all comfortable with. These cancel out, which is good. And then I just have minus, and I divide by h, 2x plus h. Some case we talked about earlier. So now you can use the theorem that tells you this limit just with the h would be 0. And then you can use the theorem which tells you if you know two limits, then you also know the sum of them. So, so this would be completely spelled out what happens here if I just write this. you look a bit confused. Okay, so that's what we get. And now we can just do the other cases. So let's do the one that is similar to this one first. And that's the one where x is greater than 0. There we can do something similar, and that is assume a function t which doesn't include 0, goes to R with t of x equals fs of x. Maybe I should use a definition sign here. Okay, and yeah, now I can do basically the same definition. Limit h to 0 of x plus h squared minus x squared over h. Calculate again 2x. Okay, and now the interesting case. What's with x equals 0? Now this case happens that you mentioned earlier, but yeah, you're busy. Okay. Yeah, now we have x equals 0. So we basically have this problem that we're approaching to 0 from different directions, and we can't really say we are only in one case. So we're really in both cases. So it's kind of oscillates between these two cases. So we cannot just calculate like here. So what do we do? I mean, we can at least try to write it down. I mean, it gets simpler because we know x is 0. So we just have something like this. Let's maybe call it plus minus h squared minus plus minus 0. So that's gone. And we divide by h. So, I mean, we could write something here. So plus minus is minus if h smaller 0 plus if h bigger 0. And yeah, for 0 it doesn't matter. So, but we declared it plus for actual 0. Yeah, but it's still okay to divide by h because it works in both cases. Yeah, so let's forget about this. So we have this plus minus h thing here, and now what is it?
Plus minus 0.
Plus minus 0, but they are both equal. So you can just say 0. I mean, at this point, I guess you could fully escalate and say, okay, sequences, proof, and for epsilon, and blah, blah, blah. Yeah, but I guess we don't have to at this place. If you reduced it down to this is obvious enough, I would say. Okay. Good. So now we have to plug it together to get a function. I mean, what they asked us is to show it's differentiable, but we know that now. So we constructed the limit in every case. And so S is differentiable, but we should state that we know that now. So make sure we get points for that. So S is differentiable because we showed the limit exists in all cases. That's enough reasoning for me. And we also know, what we know is S prime of x is the following function. It depends on the sign of x again. So in this case, we got minus 2x, and in the other case, we got 2x. So we can say, for example, minus 2x for x smaller 0, and s prime x is 2x for x bigger 0. Yeah. Okay, done so far. Let's look a bit further. Okay, they ask for the second derivative. And does it exist everywhere? Do you already have a guess?
No.
No guess, or no, it doesn't exist everywhere? Okay, where's the problem?
0, right?
Yeah, 0 is a problem, because if we draw it, we can already kind of see it. So below 0, minus 2x means it's a straight line going down, and greater 0, 2x, it's a straight line going up. So it looks like this. So that's S prime. And this is a problem because here you don't know what slope at this point should be. So yeah, let's do part D. D. Okay. So we have our idea that it probably S prime prime exists everywhere except 0. So now we should find an argument for that. I mean, picture says slope shouldn't exist. So the argument should be something like at 0, the limit doesn't exist. So we can do a case distinction again. So x smaller 0, s prime prime x. So yeah, we can just do the same calculation. Yes, it's okay. Okay, so smaller 0, same reasoning. Then plugging this in gives us minus 2x. Over here we get, I'll just write it down. X plus h, and here we get 2x over h, and that's blah blah blah. Calculating gives you minus 2x, minus 2, sorry. Okay, and in this case, you have almost the same. I mean, I guess you should, in the exam, probably be a bit more verbose here, but I'm assuming this calculating this term won't be your problem. So when you already know what cases to consider and stuff like this. So that's 2. And the interesting case is x equals 0. And what we get here, I mean, last time 0 turned out well because our function tended to 0. But this time it doesn't. There's a conflict. So it's constant -2, constant 2. So S prime prime looks something like this. So it's -2 here, and all of a sudden here it's 2. So you see a discontinuity, and that's where the second derivative doesn't exist. So you have this, and now we have to look at it in more detail. So S prime of x plus h, yeah, we don't really know what it is. It will be 2x plus 2h, but we don't know the sign. So maybe let's say it like this. And in this case, we plug in 0, so it should vanish. We also have to getting tired, I guess. So yeah, in this case, we plug in 0, so it vanishes in both cases. We don't have to care. It's 0, and we divide by h. So in the end, similar to last time, we remain just with this, and we can divide because it works in both cases, but we are stuck with plus -2. Last time we had 0, they turned out to be both the same. This time they don't. So we have a conflict here. So we have kind of two numbers here. So limit does not exist. So we could also be a bit more specific. Depends on h smaller 0 or h greater than 0. Okay, and now I guess this is also important. Don't just do the calculations, draw a conclusion from it that shows us that you know what this means. So, yeah. So you have to say something like S prime prime, or no, let's say it like this: S prime is differentiable and for all x in R, x not equal 0. Okay, and we already know what S prime prime will be. So S prime prime of x. Maybe I write it like this. I don't know how comfortable are you with this notation. It's good. Okay, S prime prime and arrow like this, and S prime prime of x equals -2 for x smaller 0 to for x greater 0. Yeah. Done. Okay, that was one exercise. I mean, I explained a lot in between, so if you really just do this, it can be a lot faster. So, but if you have any wishes, we should spend the remaining 20 minutes, please let me know.
I think it would be nice to have one example of proofs, perhaps.
Proofs, okay.
I think the next exercise is about proofs, right?
The next just, so 2, differentiability from continuity. Yeah, I looked at that. The proofs are
kind of calculational here.
Oh, okay.
So
I
it
mean,
might not be what you want to see.
Yeah, perhaps the one with the algebraic structure instead of.
Is there no example of proofs type exercise from another exam?
Proofs types exercise.
I remember thinking that chapter 2 of the book that this course was completely comprehensive. The rest of it.
I see. Yeah. So you mean a proof that happened after the completely comprehensible part, or?
I guess they weren't so clear about like the general notation of when you're using proofs.
Yeah.
Because Patrick uses like elimination rules and introduction rules, but examples weren't super clear. So perhaps something on that. I guess it's hard to come up with something from out of nowhere. I don't know if it's common to have an exam.
Yeah, I mean, we have a second session like this on Tuesday.
Okay.
So you could find one and send me, and I do it on Tuesday. I guess that's a good way to do it. And yeah, I mean, now you also said this algebraic structure exercise. I think that's from the part of the course that you declared as completely clear or something like this. So I don't know how interesting it is, but we can of course do it. So I think this is, it's good anyway. So abelian monoid, blah, 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 structure, define a type class, define a data type for expressions, find instances. And so that's the creative part, and a part where you might have to prove something. David, no, seems we have. Okay, yeah, should we do that one?
Sure.
Okay. Just make some space. Okay, yeah, an abelian monoid is, should I copy that? I guess it would be good. Yeah. An abelian monoid is a, how do they say it, a type? Oh, a set, okay, then let's call it set. A set with some operation like this and some constant like this, which will be the neutral element, such that for all x, y, z in M, we have x plus y. I guess I should do associativity the same way they do it. That's one, and for x, our neutral, that's this element. For all x, our neutral element plus is really neutral. It's usually, in this case, somewhat redundantly stated like this. And now the abelianness, which means x operated with y, is the same as the other way around.
Okay, that's an abelian monoid, and abelian is just a synonym for this one, commutative. So as you might know from abelian group, which I guess appeared in the course. And now it asks us to define a type class. So, I mean, in the style, which was common in the lecture. So that just means we have to build a type class which has these two things. So I hope I remember. Do they prescribe a name? Yes, monoid. Monoid. M means we have a function plus from M to M to M, and probably I'm not allowed to use this, so maybe I should call it op and 0, like this. Okay, that's what I would do. And now we should do, I guess there are no questions. And then we should do a data type for expressions. Maybe over here. So data, I guess, with a variable type. Yes. So data up monoid expr v, the variable type. And we can say that's either a variable or a operation on other expressions. So up monoid. That's an unpleasantly long word. V and up. So we have a constant 0, and that's it, because we don't talk about the laws, I guess. Did I miss anything? No, it's a pretty short list. But there's more text. So with variables and define an up monoid instance for it. Okay. But there's so much text, I guess I should read it. These are expressions formed from applying the monoid operations to the appropriate number of arguments, e.g. or left, all the left-hand sides and right-hand sides of the above equations.
I think they want you to declare an instance of the type class.
Yes, but I'm a bit confused about the text after it. So instance up monoid of this thing. Oh. I'm slightly unsure about the Haskell syntax. Where do I put my type argument? Probably here.
You put it after the expression, I think. Yeah, keep it.
I don't declare it.
Yeah.
Okay. Yeah. Different from it. Yeah. Okay. Good. Thanks. Yeah. And now I have to kind of give these operations, but I can just use my constructors here. Oh, so it's a small op xy is op xy, and 0 is 0. Yeah. Yeah, what's a bit maybe lame about this is if you derive EQ, this won't satisfy this equation. So it's not an abelian monoid. It's just an instance of this type class, which has this raw structure here. Okay, but doesn't matter. So the next thing asks us to find instances. That can get difficult if you problems with coming up with examples. So yeah, any guesses?
Addition on reals, I guess.
Addition on reals.
Yeah.
Yes, that's true. Okay, so we solved the first part of C. So yeah, I guess I can just write it in Haskell syntax. Instance up monoid real, where little of xy is just x plus y and 0 is 0. Good. And it has a second part which asks us now about the mathematical structures with the laws to find a monoid which is not an up monoid, so a non-commutative monoid. Yeah, that might be not so
Subtraction.
Subtraction.
What
Okay.
about matrix multiplication?
Okay, very good. Yes. So matrix multiplication works. I'm not sure if subtraction is a monoid.
What
So it's certainly
exactly
not
is-
commutative, but yes.
What is the exact definition of monoid?
A monoid is something with all this except the last one.
Okay.
So the last one is says it's abelian. This or commutative. Just this. Okay, so matrix multiplication works. Subtraction, I'm not sure, but let's just try it. I mean, it's good to think about lots of examples. So like this. I just comment here what we are doing now. Now find monoid which is not abelian. So, okay, we try subtraction. And I actually, yeah, okay. So subtraction is not associative. Yeah. So no. Minus is not associative. So this one doesn't work. Matrix multiplication. Yeah. There's okay. Okay. Chat roughly followed our discussion. So no matrix multiplication. New idea. But it's maybe not like you should write it in the exam, but I guess it's clear. So new idea, matrix multiplication. So yeah, I guess we can assume we know this is associative. So associative check. And but I guess it would be nice to have an example where we see it's not commutative. Any idea how to come up with one?
I think you have the identity matrix and also the identity matrix except one of the diagonal elements is negated. It might not be mute.
Okay, that might be a nice simple example. So let's try that. Sounds good. Okay. And now I have to remember matrix multiplication, but it doesn't look too good. I guess it's the same again, right? And the other way around.
I think I was wrong.
It can't work because this is the neutral element, so it will always be the same. Yeah. I mean, it would be kind of okay, I guess, to assume just we know that this is not commutative, just say it.
But if you have matrices with different dimensions on like n is 3 and n is 2, you flip and you get different dimensions on the result as well. That would be an easy way to show it.
Those matrices don't form a monoid.
Okay. Yeah, sure.
Because you can't multiply everything.
Yeah, that's true.
So that's a different kind of structure called category, but we don't have it in the course.
What if you had like matrix with all ones in the first row and all zeros in the second row, and then same way but for column?
I'm not sure what you mean. Once,
So if the first row was entirely ones, zeros. And what you multiply that with similar matrix except ones in the row, maybe.
I guess that's good. Like the idea.
I'm not sure.
Yeah, let's just try. I remembered how matrix multiplication works. So wait. Can that be right? Must be doing stuff wrong. Please check my calculations.
Yes, that's great.
Oh, okay. Oh, that looks good. That's nice. What, really? It's certainly different, but not entirely sure I did everything correct.
Yeah,
I'm still surprised by the result, but yes, it's extremely non-commutative here. Yeah, so check. Nice. Yeah. I guess if in doubt, just state it. It's kind of commonly known that matrix multiplication doesn't commute. Okay, yeah, and a small detail. Here we used matrices in the monoid of matrices. So these are all not invertible. So if we want to group, it is a bit harder. We can only take invertible matrices. Be different. Okay. Yeah, maybe we just have a look. What else they want? Define a general evaluator. Okay, it's also a pretty standard exercise. Assignment function. Okay, yeah, let's do that. Maybe I just erase this. So we still have our definitions here. Time. But I guess I can just write this down. This was D. So this just asks for an eval function, which takes an environment, which is a map. Okay, yeah, sure. We have to like say we have an monoid M, and then we have a function from the variable type to M, and take an expression, so up monoid x with variables from type B, and produce something in our monoid M. So that's the type of the eval function, and I guess you remember what to do here. So you just have to treat all constructor cases like if we have a variable, we just look it up in the environment. Oh, it's a bit bad to call it V. Maybe we call it name or something like this, because V could be string and then it's just variable name. And what else do we have? Op. So big op, the expression op of other expressions gets mapped to little op from our given monoid to the evaluated expressions. So yeah, nothing wild here. Okay, there was. Okay, yeah. I guess we stop here, and if you have any particular exercise you encounter or questions, you can mail it to me or try to communicate via Canvas to me. And yeah, I'll say something about it on Tuesday. Okay. Stop.
Yeah.